Swayam Prabha. Digital India. Educated India.
Hello everyone, my name is Yulin Shen. The topic of my presentation is meta-learning-based functional ODE method for monitoring continuous multimode process with irregular sampling data. Process safety and quality can be monitored by measured process data like temperature, flow rate, or pressures. In most chemical operating process, the operating condition for units should be adjusted sometimes to maintain the desired production quality. Because of seasonal change, the variability in the quality of raw materials and the equipment characteristics, it is of common occurrence to monitoring a new operating condition with few samples, which is an urgent and challenging problem for practical applications. Moreover, the measured data are easily defiled by the outside disturbance and noise. The sampling interval would be messy and irregular. By removing the contaminated samples, leading to the loss of dynamic information and the increasing difficulty of dynamic model constructions. So this will cause the traditional MSBC method cannot be applied. In order to solve the problem of the process just mentioned, we present a novel meta-learning method to establish an accurate model as soon as possible for a new operating condition with few data samples, and to address the correct data and continuous dynamic modeling problems. A model structure of the ordinary differential equation combined with the functional data analysis is proposed. Then first, introduce the multivariable functional ODE model. This model can address corrupt data and continuous dynamic modeling problems. This is an ordinary differential equation of nth orders, and the initial condition expressed as beta 1 to beta n minus 1. For each variable, assume the nth order differential can be expressed by wavelet function fitting. Then integrating the wavelet function can get the n minus 1 order differential. And A is an initial condition. Vector P is a wavelet function after integration. By analogy, the expression of first-order differential can be obtained. Finally, the ODE can be organized into this formula, and these B and C are model parameters. And next, we need to solve the model parameters, and minimizing this function is our objective function. Use gradient method to solve the bilinear problem, and lambda is the learning rate. After a series of derivations, the gradient of the objective function to parameter B and the parameter C is obtained. Iterative update these two parameters until convergent. This is the solution for single model parameters. But the gradient method generally require more iterations. If we want to quickly get the model with differential conditions, we can use meta-learning to get the good initial parameters. So this is the framework for meta-learning. Meta-learning focus on learning a good model initialized first and use it for fast learning in a new task. The aim of the meta-learning method is to train the model on the variety of learning tasks, so they can solve new learning tasks using only a small number of iterations. Next, I will describe the calculation procedure of meta-learning. Meta-learning is mainly divided into two steps. One step is to obtain model parameters of each conditions. Another step is to update the meta-parameters. To ensure data diversity, all data will be divided into supporting data set and the query data set first. The parameters for each condition are calculated from the supporting set, and the meta-parameters are updated by gradient with respect to the parameter of each condition in the query dataset. Let's move the parameters to the best position to train each condition without taking as many gradient steps. So this step is called meta-learning algorithm. This is the end of the proposed method. And then use numerical case and industrial case to verify the performance of these methods. To verify the effectiveness of the proposed method, different scenarios are used. First, the new condition is similar to original conditions. In this case, 6 groups of simulations were designed with the different operating conditions. The data is shown in these figures. The 5 data sets are used for training meta-parameters, and the last data set is used to test the performance of meta-learning, performance of meta-parameters. So using meta-parameters as initial parameters, new model parameters can be quickly converged. And we can see the black line in the figure is the prediction result of meta-parameters. Then accurate prediction result can be obtained after 90 iterations, like the red line in this figure. Without the meta-parameters, it would take 10,000 iterations to get the same prediction result. And then in the second scenario, the same training data, use the same training data, but the new condition is different from the original conditions. Obviously, the result of the meta-parameters predictions are biased, and more iterations are needed to get the accurate models. To get an accurate model, in certain conditions, there would be a majority of data. This will result in uneven amount of data. In this scenario, training efficiency will be affected. So the training efficiency is equivalent to retraining the model because of meta-parameters are affected by a large amount of data. Then we want to solve this problem. If the operating condition with large sample size and are sampled at intervals, so that the sample size is similar to most operating conditions, the effect of meta-parameters is greatly improved. Although some data information was waste, the iteration efficiency will greatly improve. and then the convergence rate is improved after adjusting the sample size to be similar across all operating conditions. So only 1/10 of the number of iterations before adjusting the amount of data. The amount of data is required to reach the convergence goal. And the data of the new conditions can also get a good model. So finally, we use an industrial case to show the performance of process monitoring. This is a PVC drying process. The data with 16 variables. The process operating conditions are changed due to variation in the concentration of raw materials and manual operations by field engineers. So the data is collected at multiple operating conditions. And the data for each condition has about 8,000 samples. There are eight operating conditions. And we see the testing data are 800 samples. Half of the testing data are used for post-training. And in the other half of the testing data, some data have a fault. So we want to check this fault by process monitoring. The prediction of the new condition models are good and they converge fast. Then using this model for process monitoring also has the best fault detection rate compared to the other methods. In this table, all three methods have appropriate FAR values, but there are significant differences in FTR. The MLFOD method has best monitoring performance, and compared with the FOD without meta-learning, the training efficiency of FOD is better and fast, and it has fast convergence rate. Finally, I'd like to recap the main points. MLFOD can directly identify models of irregular samples data by functional analysis, and the meta-learning scheme determines the meta-parameters, so the new operating condition model would be quickly obtained. That's all. Thank you for your attention. It was a pleasure being here today.